Hash functions are a cornerstone of modern computing, forming the foundation for efficient data storage, retrieval, and security. A hash function is a mathematical algorithm that transforms input data of arbitrary size, such as strings, numbers, or even complex objects, into a fixed size value known as a hash code or hash value. This hash value serves as a unique or semi-unique identifier for the input, enabling rapid data access in structures such as hash tables. Hash functions are widely employed in many areas of computer science, including database indexing, cryptography, digital signatures, checksums, and password storage, due to their ability to map large datasets into compact and easily manageable representations. The efficiency of hash functions lies in their ability to provide near constant time complexity. 1. For lookup, insertion, and deletion operations when properly designed and utilized. However, hash functions are not inherently perfect. Challenges such as collisions, where multiple inputs produce the same hash value, necessitate careful handling to maintain performance and correctness. The design of a hash function is critical for the performance of any hashing-based system. A good hash function should be deterministic, meaning the same input always produces the same hash value. Uniformly distribute keys across the available storage space to minimize collisions, and compute quickly to avoid becoming a performance bottleneck. Common hash functions include simple modular arithmetic, polynomial rolling, multiplicative hashing, and cryptographic hash functions like SHA-256 or MD5. Modular arithmetic hash functions typically calculate the remainder of dividing the key by the size of the hash table, providing a simple and efficient way to index values. Polynomial rolling hash functions, often used for strings, treat each character as a coefficient in a polynomial, applying modulus operations to keep values within bounds. Cryptographic hash functions, in addition to providing efficient mapping, are designed to resist deliberate collision attempts, making them crucial in security-sensitive applications such as digital signatures and blockchain technology. Each type of hash function has trade-offs between speed, collision resistance, and implementation complexity, influencing its suitability for specific tasks. Despite careful design, collisions are inevitable because the number of possible inputs typically exceeds the number of hash table slots. Effective collision avoidance and resolution strategies are therefore essential. Collision avoidance begins with a well-chosen hash function that distributes keys evenly. But when collisions occur, specialized techniques are required to resolve them. The two primary approaches for handling collisions are separate chaining and open addressing. Separate chaining involves storing multiple elements that hash to the same index in a linked list, or another secondary data structure. Each hash table slot contains a pointer to the head of a linked list of entries sharing the same hash value. When a collision occurs, the new element is appended to the corresponding list. While separate chaining is conceptually simple and can handle an arbitrary number of collisions, it introduces additional memory overhead for pointers and can degrade performance if long chains form due to poor hash function design. Nonetheless, with a properly sized hash table and a good hash function, separate chaining typically maintains efficient average case performance, allowing 1. Insertion and lookup in practical scenarios. In contrast, open addressing resolves collisions by probing the hash table to find an empty slot for the new element. In this approach, all entries reside within the hash table itself, eliminating the need for linked lists. Open addressing requires a systematic probing sequence to determine subsequent positions when a collision occurs. Several probing strategies exist, including linear probing, quadratic probing, and double hashing. In linear probing, when a collision occurs at index I, the algorithm checks the next sequential slots, I+1, I+2, and so forth, wrapping around to the beginning of the table if necessary. Linear probing is easy to implement and maintains good cache performance because of the sequential memory access pattern. However, it suffers from primary clustering, where consecutive occupied slots increase the likelihood of further collisions, potentially degrading performance in densely filled tables. Quadratic probing addresses the clustering problem by using a quadratic function to determine the step size in the probing sequence. Specifically, after a collision at index I, the algorithm probes I+1 to the power of 2, I+2 to the power of 2, I+3 to the power of 2, and so on. This nonlinear probing reduces clustering and spreads colliding elements more evenly across the table. Quadratic probing still requires careful table sizing, typically a prime number, to ensure that all slots are eventually probed and that no positions are permanently unreachable. One limitation of quadratic probing is that it may not always guarantee that an empty slot is found. If the table is nearly full, necessitating load factor management to maintain efficiency. The load factor, defined as the ratio of elements in the table to the table size, is critical for both linear and quadratic probing. High load factors increase the likelihood of collisions, leading to longer probe sequences and degraded performance, whereas low load factors waste memory but enhance efficiency. Beyond these basic probing strategies, advanced open addressing methods like double hashing further improve collision resolution. In double hashing, a second hash function determines the step size for probing, making the sequence of slots visited for each key unique. This technique reduces both primary and secondary clustering and is especially effective when the hash table is densely populated. Additionally, open addressing requires careful handling of deletions. Removing an element in open addressing is more complex than in separate chaining, as a simple deletion may break the probe chain, causing subsequent lookups to fail. Typically, deleted slots are marked with a special sentinel value to indicate that they are available for insertion but cannot terminate a probe sequence. Properly managing these sentinel values ensures that search, insertion, and deletion operations continue to function correctly. Hash tables, together with hash functions, play a pivotal role in numerous computer science applications. They provide the underlying mechanism for associative arrays, symbol tables, compiler implementations, caching systems, and database indexing, where efficient insertion, lookup, and deletion are essential. In networking, hash functions are used in routing tables and load balancing algorithms, while in security, cryptographic hash functions ensure data integrity and authenticity. The choice of collision resolution strategy, probing method, and load factor management significantly affects the performance and reliability of hash-based systems when designed carefully. Hash tables can achieve average case constant time complexity, offering unparalleled efficiency for dynamic datasets. The interplay between hash function design, collision avoidance, and resolution strategies highlights the importance of both theoretical understanding and practical engineering in deploying effective hash-based solutions. In conclusion, hash functions are fundamental tools in computer science that transform complex input data into fixed-size identifiers, enabling efficient storage and retrieval in hash tables. Collisions, while inevitable, can be effectively managed using separate chaining or open addressing, with linear probing, quadratic probing, and double hashing providing different trade-offs in terms of simplicity, clustering reduction, and performance. Careful attention to hash function quality, table sizing, and load factor ensures that hash-based data structures maintain their efficiency across diverse applications. By understanding the intricacies of hash functions and collision resolution methods, programmers and computer scientists can design systems that are both robust and high-performing, making hash-based structures indispensable for modern computing challenges.